The cosmos beckons. It always has. For millennia, we have looked up at the moon, our silent, glowing neighbor. We've dreamed of it, written poetry about it, and in a fleeting moment of history, we even walked upon its dusty surface. Now we are poised to return, not just for a brief visit, but to stay. This grand ambition requires something more than just rockets and landers. It requires power, abundant, reliable, and continuous power. This is the challenge that has led NASA to a bold and necessary conclusion. The future of a sustained human presence on the moon hinges on a technology we have harnessed on Earth for decades: nuclear power. It is a monumental step, one that redefines our relationship with our celestial companion. Today, August 8, 2025, we stand at a pivotal moment. The directive from Acting NASA Administrator Sean Duffy is clear and ambitious: establish a functioning nuclear reactor on the lunar surface before this decade is out. This is not merely a scientific experiment, it is a foundational piece of infrastructure. Imagine a lunar outpost, a hub of research and a stepping stone to Mars and beyond. Such a base cannot simply power down when the sun sets. The lunar night is a formidable obstacle lasting for 2 long, frigid weeks. To survive and thrive, to conduct meaningful science and support human life, we need a power source that is completely indifferent to the rising and setting of the sun. Nuclear fission offers that promise of unwavering energy. The scale of this endeavor is unlike anything we have attempted before. Past robotic missions, like the venerable Voyager probes launched in 1977, used a different kind of nuclear technology. They carried radioisotope thermoelectric generators, or RTGs. Think of these as nuclear batteries, slowly releasing heat from the natural decay of plutonium to generate a modest amount of electricity, enough to power their instruments across the vast emptiness of space. But a human habitat with life support, rovers, and advanced scientific equipment requires orders of magnitude more power. The proposed lunar reactor aims for at least 100 kilowatts of electrical output, a stream of energy robust enough to power dozens of homes back on Earth. This leap in power generation is what transforms the dream of a lunar base into a tangible engineering project. It's the difference between a campsite and a city. With a steady flow of nuclear energy, astronauts could melt ice locked in polar craters to produce water and breathable air. They could operate heavy machinery to build permanent structures using lunar soil, a process known as in situ resource utilization. They could power sophisticated laboratories to unlock the moon's secrets and prepare for the even longer journey to Mars. This isn't just about keeping the lights on, it's about empowering a new era of exploration and creating a self-sustaining human foothold beyond our home planet. When we think about power in space, our minds often jump to solar panels. They are iconic. We see them unfurling from satellites and stretching across the International Space Station. For many applications, solar power is a brilliant and effective solution. It harnesses the most powerful reactor in our solar system, the sun itself. However, the moon presents a unique set of challenges that severely limit the practicality of a solar-only approach for a permanent base. The primary issue is the long, unforgiving lunar night. For 14 Earth days at a time, any location on the moon is plunged into total darkness and extreme cold. Enormous, heavy, and complex battery systems would be needed to store enough energy to survive this period. The sheer scale of a solar and battery system required to match the output of a nuclear reactor would be staggering. You would need vast arrays of solar panels covering an area equivalent to multiple football fields just to gather enough energy during the lunar day. Then you would need an equally massive and heavy battery farm to store that power. Launching all that mass from Earth would be incredibly expensive and logistically complex. Furthermore, the fine abrasive lunar dust, or regolith, is a constant threat. It could coat the solar panels, drastically reducing their efficiency and requiring constant maintenance from astronauts, which is a risky and time-consuming activity. A nuclear fission reactor, by contrast, is a model of efficiency and compactness. A system capable of generating 100 kilowatts could be designed to be small enough to be transported on a single lander. Once deployed, it just works. It does not depend on the angle of the sun or the time of day. It provides a constant, predictable stream of power through the bitter cold of the lunar night and the heat of the lunar day. This reliability is the single most important factor when human lives are at stake. It ensures that life support systems never falter, that experiments can run uninterrupted, and that the habitat remains a safe haven against the harsh lunar environment. This is not to say that solar power has no role to play. A hybrid approach is likely the most sensible path forward. Solar panels could be used to power rovers on short excursions during the lunar day, or to supplement the power grid for non-critical systems. This would add a layer of redundancy and flexibility to the overall energy infrastructure. But for the core functions of a permanent human outpost, for the essential life-sustaining systems that must operate around the clock, the steady, powerful heartbeat of a nuclear reactor is indispensable. It is the bedrock upon which we can build a lasting presence on the moon. Placing a nuclear reactor on the moon is not a simple task. It's a monumental engineering challenge that pushes the boundaries of our technological capabilities. The first hurdle is designing a reactor that is not only powerful, but also incredibly compact, lightweight, and rugged. It must withstand the violent vibrations and immense G-forces of a rocket launch. It must then survive the journey through space and a soft landing on the uneven lunar surface. Companies like Lockheed Martin are already deep into the design phase, developing concepts for fission surface power systems that meet these stringent requirements. The reactor must be built with materials that can handle extreme temperature swings from scorching daylight to cryogenic night. Once the reactor arrives on the moon, the next challenge is deployment and activation. The system must be designed for remote or autonomous setup, or at the very least, for easy assembly by astronauts in bulky spacesuits. The reactor will likely be delivered to the surface and then transported a safe distance away from the main habitat before being activated. Safety is paramount. The reactor must have multiple redundant safety systems to prevent any possibility of a critical failure. It will need to be shielded to protect the astronauts and sensitive electronic equipment from radiation. Engineers are exploring innovative solutions, such as using the lunar regolith itself as a natural shielding material, burying the reactor to contain its radiation. The benefits, however, far outweigh these technical hurdles. A reliable nuclear power source completely changes the game for scientific research. Current robotic missions are severely power constrained, operating on just a few hundred watts. Imagine what we could achieve with kilowatts of power at our disposal. We could drill deep into the lunar crust to study its geology and history. We could operate powerful telescopes on the far side of the moon, shielded from Earth's radio interference. We could run complex experiments in materials, science and biology, taking advantage of the unique lunar environment. This abundance of energy elevates our scientific ambitions from mere observation to active, large-scale experimentation. Furthermore, the technology developed for a lunar reactor has profound implications for the future of space exploration. The same principles of compact, efficient fission could be applied to nuclear thermal and nuclear electric propulsion systems. These advanced propulsion methods would be far more efficient than the chemical rockets we use today, drastically cutting down travel times to Mars and other destinations in the solar system. A trip to the red planet that currently takes 6 to 9 months could potentially be shortened to just 3 or 4. Powering our bases and powering our ships, this single technology is a key that unlocks the entire solar system. The race to place a nuclear reactor on the moon is not just about science and exploration. It is deeply intertwined with geopolitics and national prestige. We are in the midst of a new space race, one that is more complex and involves more players than the first. As acting NASA Administrator Sean Duffy has pointed out, there is a very real concern that the first nation to establish a powerful energy source on the moon could set the terms for future access. They could potentially create keep-out zones around resource-rich areas, such as the water ice deposits at the lunar South Pole. Securing a foothold for the United States is therefore seen as a matter of strategic national interest. This sense of urgency is amplified by the actions of our international competitors. China and Russia have publicly announced their own joint plans to construct an international lunar research station. A key component of their architecture is also a nuclear reactor to power their base. This direct competition has put pressure on the US to accelerate its own timeline and demonstrate its continued leadership in space. The moon is no longer just a scientific destination, it is becoming a domain of strategic importance, much like the high seas or the airspace of Earth. Establishing a power infrastructure first is a way of planting a flag, both literally and figuratively. The Artemis Accords, a set of principles for cooperation in the civil exploration and use of outer space, are designed to promote a peaceful and transparent approach. However, the reality is that competition often drives innovation and progress at a faster pace than cooperation alone. This new space race, while carrying strategic undertones, is pushing NASA and its commercial partners to solve difficult problems and to do so quickly. The 2030 deadline is not just an arbitrary date. It is a clear signal to the world that the United States is committed to leading this new chapter of human expansion into the cosmos and ensuring that the principles of open and peaceful exploration prevail. Ultimately, the development of lunar nuclear power will have implications that ripple across the globe. The nation that masters this technology will not only secure access to lunar resources, but will also gain a significant technological advantage for future missions to Mars and beyond. It is about ensuring a future where humanity's expansion into space is led by democratic values of openness and collaboration. By pioneering this critical infrastructure, the US aims to set a precedent for responsible and sustainable development on the Moon, creating a framework that allows for all of humanity to benefit from our journey back to the stars, and eventually our voyage to the worlds that lie beyond.